Okay. Thank you all for joining us for this TSVP talk. Today's speaker is Brian Kenji Iwana, who is an associate professor at Kyushu University. His research includes pattern recognition and machine learning. Specifically, he works with artificial neural networks, time series recognition, image recognition, and natural language processing. So please, Brian, tell us more about machine learning with less data.
Thank you. Okay, yeah. So I'm going to talk about machine learning. You can hear the mic's okay? Okay, I'm going to talk about machine learning with less data and hopefully introduce some of my research. So like I mentioned, so after my introduction, so I'm from America, and I went to the University of California, Irvine, and then I was a software developer for a while, and I worked at NASA. And then I came to Japan to get my PhD, and then now I'm an associate professor at Kyushu University. And in case you guys want to know, Kyushu University is in Kyushu, which is the southern part of Japan, but I guess not as southern as Okinawa. And this is just an introduction to my lab. So in my lab, we have two professors, Professor Yoshida and Bise Sensei, and we have two associate professors and three assistant professors and a huge amount of students. In our lab, we study machine learning theory and especially neural networks and deep learning, and we deal lots of different topics in image recognition and time series, and there's so many different areas that we study. But in general, this is maybe a little bit different kind of a talk from other professors. So other visitors might have like some findings and some science things, like, I don't know, like a new chemical or something. But in our research, we really care about the algorithm. So we create new algorithms, and it's more like engineering in that sense. Anyway, yeah. So before I get into it, I need to give a small little introduction, very, very brief introduction on pattern recognition and machine learning. So first, we'll start with an easy case. On this side, we have a human, and on this side, we have a computer. And then in this easy case, we want to show them, or if we show each one what fries are, like this is a picture of fries, French fries, there'll be no problem. So when we show them each this fries, then they'll learn what it is. And then if we show them another picture of French fries that's slightly different, then both, obviously the human and the computer can both recognize that these are both fries, right? When I switched this page, you immediately knew it was the same thing. But there's some slight problem with computers. And the problem is that if you show something that's slightly different, like significantly different, then maybe the computer will have trouble. So it's easy for us humans to recognize that the fries were taken out of the box and poured on a plate. But it's not so easy for a computer to internalize that these things on this plate are the same thing, just poured on a plate, right? It's significantly different. So this is trouble that computers have. So why do we even use machines? Like, why machine learning? What's the point? And the main reason is because computers are computers. They won't complain. So we can throw tons and tons of stuff at a computer, and the computer will have no trouble or no, it'll just crunch through it and identify everything. Whereas if I give you each of these small little pictures to a human, maybe get past 10 and then get mad. Right? So this is why we use machine learning. It's so we can do tasks like that humans won't want to do. Okay. And roughly, skipping everything, this is just a general diagram of what machine learning is. So in general, machine learning is all about taking a bunch of data, giving it to a machine, and the machine will create some internal mapping, and this mapping will make a decision. So in this case, I'm taking a bunch of pictures of fish and cars, throwing it to a computer, and the computer will learn that this is what a fish is, and this is what a car is, right? This is called decision boundary, and this is just the decision made from the model. Okay? Okay. So now backing up even more, so there's a little some history. So first, we have classical machine learning. So for a long time, all the way the 1700s, I think Bayes is from the 1700s, we have classical machine learning. And in classical machine learning, there's generally these two basic methods. One is distance-based methods. So these are methods that can make decisions based on how the proximity to other data points. And then another one is called discriminative methods. These discriminative methods, they're methods that maybe create an internal model and that can make a decision. So for example, this is called a SVM, a support vector machine. And in this case, it uses like the gap between data to make the split, the line. Right? It's not important that you know how it works, but what's important is that, this is for a long time, these kinds of methods were the standard. And now we call it classical machine learning and not just machine learning because nowadays we have something called artificial neural networks. And I'm sure all of you have heard this word artificial neural network or read that, like you've heard of it in regular life because it's become so normal now. But actually, artificial networks are really old. They're some of the earliest classifiers and the earliest machine learning models were neural networks. Like this multi-layer perceptron. This is like the classic idea of what a neural network is. If you like Google neural network, you'll see something that looks like this. This was actually proposed all the way in the 1960s or 1950s. So so the neural networks are really old. But and then these are just some of the landmark networks all the way through history. Anyway, so the reason why it's called an artificial neural network is because it's kind of similar to how a biological neural network works. So in a biological neural network, we have neurons, and the neurons are like this, right? We have some kind of actually, I'm not a biology person, so I don't know. But anyway, this is a neuron, and we have like a synapse and the dendrites. And anyway, it takes a bunch of data and combines it to have an output. In the same way, a neural network does something similar. So in this one isolated thing, neuron or perceptron, this is a simple operation. Actually, it's just a simple summation. So this sums the inputs together and then puts it through some function and then spits out some output. Anyway, so this one single neuron is like a biological neuron, and then an artificial neural network is just a bunch of these small little operations smashed together, and just like a brain. But anyway, so the reason why you know of neural networks and not the classical machine learning is because something changed. And this change happened actually really recently. So up until probably XGBoost, classical machine learning was the state of the art. So like, for example, when I first got my PhD, no one used neural networks. Even though neural networks have been here for 30 years before me, no one used it because everyone was using random forests and SVMs and the classical methods, because this is what was the best. But something changed, right? So what changed? Why did all of a sudden now, if you go to a machine learning conference, you won't find a single classical machine learning paper? They're 100% neural networks now. And there's a reason. Anyway, besides the empirical reason. So what changed about this? What changed is what I consider the three major events that made this change. And the first one is NVIDIA released something called CUDA. CUDA is just a library that allows GPUs to be used for machine learning. So up until here, GPUs were used for like games, but then after NVIDIA released CUDA, now people can use the power of a GPU and do many calculations really, really fast, right? Really small calculations. So this was one huge step. The next step was large data sets were being created and open to the public. So for example, ImageNet is a really famous image data set, and it has 3.2 million images. So up until this point, most data sets were fairly small. But with the introduction of these huge data sets and the huge ability to do calculations, now we can like leverage huge amounts of data and actually develop really complex and huge models. And the last major event is like in was something called AlexNet. So like before AlexNet is a type of convolutional network. I won't explain that today, but if you're interested, maybe tomorrow I'll have an introduction to machine learning. But today I won't explain why. But there were many CNNs before. So this is like the first CNN, Linnet or whatever it is, all the way back here. But they still weren't used until AlexNet. AlexNet was the first time it showed that if we use GPUs with this huge amount of data, we can get better than human performance. And this was a huge turning point. After this point, then people moved to neural networks, to what we have today. Anyway, yeah. But maybe some people might fight me on this, but this is what I think was the big turning point. Yeah. Now, every day, everyone uses neural networks. Okay. Yeah. So now that brings us today. So today, these are some amazing things that we can do with neural networks, like ChatGPT. I'm sure all of you use ChatGPT, and there's self-driving cars, and you can generate images. I actually generated this image for today, but maybe I don't look like that. Yeah. Anyway, yeah. So, yeah. So underneath all of these methods are neural networks. But there's something else hiding underneath these networks, and that's the data. So ChatGPT 5, I think it's one of the newest ones. It was trained on 250 terabytes of data or of text. That's an insane amount of text. And Waymo, which is what Google automatic driving became, is trained on 500,000 hours of driving. And then image generation is millions and millions of images. So while these are very powerful tools, they're tools on the backs of huge amounts of data. All right? Okay. And just to give some more background on why data matters, just some more theoretical. So data matters is because kind of the law of large numbers. So as the amount of data increases, the better of a model you can learn. So for example, on this side, we have only these 6 points and then some unseen data. With only these 6 points, the model, this split between the red and the blue, this is a very poor model of the data, right? It fits the red and blue well, but then under unseen data, it's poorly, right? So this belongs with the blue. But as you increase the amount of data, like large law numbers, and as you increase the number of samples, you can get a better mean. So as you increase the number of data, you can get a better model. So with this amount, we can maybe learn a better split between the classes. And in this case, the green is correct, right? Okay. Sorry, maybe I'm going too fast. So anyway, but actually, so this idea that data matters a lot it's been known for a long time. So there's this famous paper called Banco Brill, they wrote this paper, Scaling to Very Large Corpora, very, very large corpora for natural language disambiguation. They found in 2001, they found that you can increase the accuracy of a model just by adding more data. So they changed nothing in the model, just added more data, and they could increase it from like 75% all the way to 90-something%. And this small change, right? So this is all the way from 2021. This is before the big revolution that I showed earlier. Yeah. And actually, something interesting about this paper, so this is 2021. Interesting is that what they called in the paper is very, very large corpora is only 1 billion words. And now in LLMs, we use trillions of tokens or trillions of word pieces. So while this was very big back then, now you can imagine that our data is 1,000 times this, or more than 1,000 times this what they had back here. Okay. Yeah. And this is kind of more background on the reason why neural networks struggle with data. So the main reason is there's these things called generalization versus memorization. Sometimes it's called variance or bias variance trade-off or other terms, but the general idea is that so generalization is when you learn a model that can generalize well. It can't, sorry, that's a loop. Generalization, it makes a model that can create a general internal idea of the data. So for example, this straight line, while this straight line is maybe inaccurate, right? It has these two red ones over here. It's not necessarily bad because, for example, it's more robust to noise. So like in the case, this kind of case, right? A straight line might be better than this curved line. This curved line fits the data well, but a straight line might have been better because it would include the green dot, right? And this is, anyway, this is called, even though it's called underfitting, but it's still, sometimes it's desirable. On the other side, we have memorization. Neural networks are really good at memorization. Memorization is when the model learns the data exactly. So for example, this line totally perfectly incorporates the data. And while this is desirable for other reasons, like being able to map complex spaces and stuff like that, it's also undesirable because it's because maybe this line is too complex and it overfits. It tries to learn too much. So maybe it shouldn't be this like wiggly. Anyway, so a good classifier learns the balance of both. And the big problem with having small amounts of data is that since neural networks are already very good at memorization, the neural network will tend to just memorize the training set when the data is small. And if it memorizes the training set when the data is small, then it'll be bad at generalization. It'll be bad at unseen tasks or other tasks, right? So so you want to balance both. So maybe most of this, most methods try to do this or to balance this. Okay, so that brings us to the actual topic of this presentation. And the actual topic is about overcoming data problems. So this is a super common problem. So me as a machine learning researcher, for me, I have access to large data sets and like mostly public data sets, and I can develop algorithms. But then maybe many of you are you're scientists and researchers, you have small amounts of data. Maybe you have like 100 or 200 or even like 10 observations of something. And and you always hear machine learning is so great. I want to use it, but I don't have enough data. So that's where I'm going to show you some methods to overcome this problem of data. Okay, yeah. And so this is just a summary. I'm not going to go through it so detailed, but just in general, these are just some methods of dealing with limited data, like data augmentation, transfer learning, semi-supervised learning, weakly supervised learning, regularization, efficient models. I'll go through each one of these right now, so it's not important. Okay, yeah. So going through each one. So the first one is data augmentation. So the idea of data augmentation is that so when we have a small amount of data, we want to increase the size of the data set. But we can't just get data from anywhere. We have to, for data augmentation, the idea is we create the data. So we supplement the small amount of data with some generated data. And in this case, so you can see we have the bad classifier, but then when we add the fake data piece, the synthetic data, then all of a sudden now we can learn something better, right? And usually, almost every data augmentation method, it creates these data or these new data points from the original data. So it takes some small data, either through transformations or generative models or something. It'll create some augmentation, or it'll create new data from that, and then adds it together, and you train the model. Anyway, yeah, the next idea is called transfer learning. In transfer learning, this is a super common method that that we've used all the way since AlexNet. And the idea is that we can transfer knowledge from one task to another. So, for example, in this side we have we train this network with some large general data, and then use the feature extractor with some more specific, smaller task data that we have less of, right? So in this case, we have the general. We can train it to classify cat versus airplane, but then we can take this feature extractor and use it for something like flow and something else, or some physics model, right? And a key point of transfer learning is the tasks don't need to be the same. The main thing we're trying to learn is the feature extractor. So yeah, the actual task on top, it could be different. Then the next type of or the next thing that you might want to do, you could do, is something called self-supervised learning. This is just this is the same thing as transfer learning. The only difference is that very recently, self-supervised learning became popular because GTP models and language models are trained using self-supervised learning. The only difference is that instead of using a labeled data set, like a large labeled data set for the feature extractor, in self-supervised learning, you don't need your own labels. You could use unlabeled data, and the way it trains is it creates its own labels. So like, for example, next word prediction. This is the most popular now with language models. But there might be other things like transformation prediction, or like something like sim CLR, and there's many different methods, but basically creating labels from the data itself. And then another area is something called like semi-supervised learning. And this one I'll explain later. But basically, semi-supervised learning is taking small amounts of data and then adding unsupervised data to help the model. I'll totally explain this later. So yeah, I'm gonna skip. And then there's weakly supervised learning. Weakly supervised learning is the idea of using weak labels. So easy to get general labels. For example, like these groups are one label. And then I'll also talk about this later in some example research. And then regularization methods. There's tons, and there's a billion papers and a billion different methods, but these all basically do the same thing. They want to increase generalization to prevent memorization by like normalizing things or adding some randomness or stuff like that. But I won't cover this today. Okay. So now I'll move on to, is there any questions or anything? Okay. So I'm going pretty fast. So now I'll cover some of my my own research. So the first is model selection with shapelet-based distance measure for a multi-source transfer learning in time series classification. Okay. So yeah, so I said I'd mention anyway, that's the next one. Okay. So anyway, again, transfer learning is, the idea is we want to pre-train some model and transfer it and fine-tune it on your own data, right? But so in general, it works well. So with the small data, you get some accuracy, for example, 81%. And then with transfer learning, you can get like a higher percent. But there's a problem with transfer learning. And the problem is that not every data set you train with is equal. So for example, if I train with this orange data set, I can get a 89% accuracy at the end. But if I train with a blue data set, I can get a 95% accuracy, right? And so, yeah, and the really big problem is that it doesn't just stop with these two. There's an unlimited amount of data sets. And how can you pick the best one, right? So it's unreasonable to train the model with every data set and then fine tune it with your data set that you want, and then see this is the best accuracy, right? It's totally unreasonable. It's impossible, right? So we need a way to predict how you can pick the best the best data set to transfer with. And there's a whole field called transferability estimation. And in transferability estimation, it tries to solve that problem. It tries to predict the effectiveness of transfer learning without actually doing the transfer learning yet, right? So it looks complicated, but simply the way it works is that you pre-train a model with the data set, and then you switch the data set to your small data set, but you only test. You don't pre-train or pre-train. You don't fine-tune. You just test it, and then you see the output distribution. If there's a lot of information by some metric, for example, this metric, if there's a lot of information learned, then it's a good model. And if there's if it's just random, then it's a bad model. And that's basically the idea behind transferability estimation metrics. The real general idea is that something is learned in here. Whether this something is related or not is unknown. But using transferability estimation metrics, we try to see, was there anything learned? Maybe it's not good, but was there something? And yeah, so anyway, that's the purpose. But maybe you saw there's still a problem with transferability estimation. And the big problem is that you still need to pre-train all these networks with the data. So you didn't really get out of it. You just shortcut the end, the fine-tuning, but you didn't escape the pre-training the billion models. So even though it's a big field, they all do terribly. Or I mean, they all have the flaw. We still need the pre-trained model. Anyway, so in my research, the main focus of the topics that I mostly work with is I work with time series. And so in this paper, we targeted time series classification. So this is a time series. Time series is just data over time. You're probably most familiar with like a sensor or audio or stock prices. These are common time series. And yeah, so the key point of our key thing about time series is that they're sequences, right, of data. Anyway, so there's this thing in time series called discriminative shapelets. Discriminative shapelets are little pieces of the time series. So for example, this circled orange, these are called shapelets. They're just pieces. And discriminative shapelets are shapelets that are important to the class. So these are 3 time series of class A. These are 3 time series class B. This little bottom part is unique to class B. And then this upper edge is unique to class A. So these are discriminative shapelets. Anyway, so in our research, we used, I skipped a slide. So there's this method, or there's this thing called shapelet discovery, where you can extract the discriminative shapelets. Again, I won't go in detail how it works, but we use something called matrix profile and just in a small classifier to find these discriminative shapelets. The important thing is that these shapelets are important to the class, and then they're small. So the general idea, or the cool thing that we found, is that if we compare these small little pieces of the data to each other, right? So these are very small little pieces. If we compare it to the small data, when 2 data sets have similar shapelets, so right, these all curve up, and these curve like mountains, then when they're similar, they can transfer the knowledge better, right? So the good thing is nothing here uses a model, right? So all this calculation is done between the data sets. So the really cool thing is that now, using these little pieces of time series, we can compare data sets to each other without a model, right? So we can now, it allows us to compare this small data with any data set very quickly, within like a minute or two. We can determine, will this data set be good for our pre-training, or will it be bad? And then we can pick the best one and then use the best one to train our model. Yeah. And in this paper, the really cool part is that it requires no training. So every new model, it requires no extra training. And whereas if you in normal methods, they're very slow. You have to train on all the data sets. And then for every new target data set, it's also very fast. We just have to look at our database of shapelets and compare, and we can know, will it be bad or good? Whereas in normal transferability measures, you have to use inference and GPU and still try. So anyway, so yeah, so this was our cool finding. Okay. So the next work is domain adaptation for UC severity estimation and patient level diagnosis. The next slides are kind of sensitive, so if you're screaming, I would look away for the next slides. Okay, so yeah. Anyway, okay. So there's a type of transfer learning called domain adaptation. Domain adaptation is a form of transfer learning that addresses something called domain shift. And domain shift is when you have one data set and the data distribution of the new data set is different. So for example, here we have real life pictures of animals, and here we have cartoons, right? So in this case, if I train this model on real pictures, it'll have a perfect or a good accuracy. But if I use the same model with no extra training, it'll have a bad accuracy, but still okay, but bad on some other images, right? So yeah, this is called domain shift, right? The data domain shifted. So yeah, so for example, in this case, we have the solids, they're the real images, and then we have the target domain, which is these data points, and then the classifier. So the goal of domain domain adaptation is to take these distributions and merge them and make them the same. So in this case, we can use the same classifier for both types of data, right? So we want to make the distributions match. And to make it a little more harder on ourselves, where we want to challenge unsupervised domain adaptation. So in this case, it's an easy case of you could just move these triangles to these triangles, right? But what if you don't have the labels? What if you don't know the labels of the second distribution? Then how do you know which of these belong to this one, which of these belong to this one? You can't know. So yeah. So this is the problem. So usually in domain adaptation, how it works is that we still want to train our model with the feature extractor and the classifier, but in this case, we want to we want to update the feature extractor so that the distributions match while freezing the classifier, right? So we want to use the same classifier for both data, but we want the way these points are represented to lay on the same space as the other domain, right? So in that case, I'm using fire to represent I'm training this, and then the snowflake to represent that this is frozen. And there's many methods that do it. So the most common method is something called adversarial domain adaptation. And adversarial domain adaptation, the idea is that we can make these distributions match using something called a discriminator or domain classifier. So maybe the easier way is to look at this side first. So in something called domain adversarial neural network, what happens is that the classifier is trained with the feature extractor, just like this, except that there's a second network called the domain classifier, and the whole point of the domain classifier is to judge are these two, or which data set did the data come from? If it came from one data set, like the real or the source data set, or the target data set. And the idea is that with this classifier, we can make it so it's indistinguishable. So the feature extractor will extract the features to make it indistinguishable between the two domains. And so, yeah, so that's an easy way to understand. And then another really famous method is adversarial discriminative domain adaptation, which is very similar. So it first trains the classifier on the source, and then it has a discriminator to train the target feature extractor to match the source, right? Or at least match it is similar enough. And then you can use the new feature extractor with the old classifier, right? Okay. I hope that was not too difficult to understand. Okay, anyway, so now my real problem. So like I said, we have lots of types of data. So one of the collaborations I have is with medical data. And in this case, the goal is we want to classify the severity of ulcerative colitis. And it's judged based on a ranking skill, or a ranking. So there's a score called Mayo. So Mayo 0 is normal, Mayo 1 is mild, then moderate, and severe, right? So we have data that's ranked kind of like this. And we collect the data from a hospital, and we have a bunch of these images, right? The first problem is that when you change to a different hospital, the imaging equipment is different. Maybe the way the setup is different, the doctors are different, everything is different about the new hospital. But the data is similar, right? So maybe like for example, the color is shifted on these two different equipments. But the problem, what happens is that if we train our model based on the first hospital, when we apply our model to the second hospital, all of a sudden the model's not very good. We have big misclassifications. The next problem we have is that getting the data is very difficult. So usually the data is like about 40 images of colonoscopy, through the body. But for a doctor to identify every image in the 40, it takes a long time, right? He has to look at the image and say, this is a 1, this is a 0, this is a 0, maybe this is a 3. That takes a long time. It takes too much time. So in real life, what doctors do is they just look at the whole set of 40 images and say, this person is a 3, or this person is a 2. Whoa. Okay, this person is a 3 or 2. So in real life, they just assign one label for the whole set, the whole patient, based on the highest severity. So in this scenario, the highest is 3, so he selects the 3. So in our real problem scenario, it looks more like this. We have hospital 1, where we have nice, good data, which each image is classified. But then we have hospital 2, which has different equipment and very vague data. So this is weakly supervised learning. I mentioned it. So yeah. So instead of individual images classified, we have entire patients classified. So each color is, this person is a Mayo 0 person, is a Mayo 1 person, and so forth, right? And so now we're combining full supervision and weekly supervision. We want to be able to, we want to be able to identify the slides of this one with the information that we learned from the first hospital. Okay, so this is our solution. So, or part of the solution. So the first observation that we had is that when we judge a person, we know the highest rating that this person has. So this person, we know this person has somewhere in here is a Mayo 1, right? It's somewhere in here is a green. But then when we classify it, we can see that, our classifier says this data point is a Mayo 2. So we know this data point is wrong, right? So so we can already find some wrong data in if we just straight apply the classifier. So our idea is that we use a method called triplet loss to move the data points so that they fit the data better. So we move it from this class, how it would have classified it, to where it belongs. And by doing this, we can fix the problem. We can we can align this data to be aligned with the classifier from the other hospital. And so we do it. We use some method, and it's too much to look at, and I think I'm running out of time. So the important thing is that we proposed using multi-instance learning with domain adaptation, and we proposed the new max severity triplet loss and some aggregation token. And we were able to perform much better on this cross-hospital stuff. So we have two hospitals, LIMUC, which is a public data set, and then our own data set from Kyushu University. And so we're able to do this domain adaptation much better. Okay. And actually, so again, in my field, the algorithm is more important than the data. Well, the data is important, but you know what I mean. So we can apply these ideas to many different areas. So I have another work that applied this area to language. So we can use this domain adaptation plus weekly supervised learning for classifying language also. Yeah. Anyway. Okay. And then the last topic is negative pseudo labeling for using class proportion for semantic segmentation in pathology. And I'm going to introduce a new problem. And this new problem is called whole slide image cancer detection. And in this problem, there's these things called whole slide images. They're slices of tumors, right? So this is just a slice of tumor. The problem is that these slices of tumors are gigantic. They're 100,000 pixels by 500,000 pixels. So this is too much for not just a model. This is too much for a human to annotate. So like a doctor to identify this part of the cell is this kind of cancer, this part is this kind of cancer. This takes hours or days just to do one slide, right? So you can see that this is a huge problem. But it's also very important, right? We want to be able to identify the regions of this which kind of cancer. So the solution to this is that in whole slide or WSI cancer detection, we can break up this image into small patches, and then these small patches look like this. And then instead of doing an entire segmentation, we can classify the small patches and then rebuild the segmentation afterward. So that's generally how we solve this problem. Anyway, but it's still a really difficult problem because getting this one slide, again, takes doctor hours or days to make this one slide. And machine learning, like before, requires lots of data. So how do we overcome this? And I mentioned or semi-supervised learning. So this is the general method this is the method that we propose to overcome it. And we use semi-supervised learning. So combining unlabeled data with labeled data. So the doctor can, in the labeled data, the doctor can identify a handful of slides. Like I think we use like 10 slides, and they can identify the cancer 10 slides, and then we can use easy to get data. So these are just slides with no doctor needed. We can get as many of these as we want, and we want to combine it. So I'll show you how to actually combine it. So the way it works is that we use something called pseudo labeling. So how pseudo labeling works is that first we take this small amount of data and train a machine learning model, a pretty weak model. And then you use the machine learning model on the unlabeled data, and you create these things called pseudo labels. These are like fake labels. And these fake labels maybe are good, maybe they're bad, but there's labels. And then you can add these labels back to the data set and then retrain the model using all the labels. So now we created a bunch of new data. And this is the general idea behind semi-supervised learning. But like everything, there's a problem. There's always problems. And the problem with semi-supervised learning is that how do we determine what a good label is? Like, can we trust these labels? Like we used this weak or this small amount of data to train this bad classifier to make the supervision for itself. But are these even good to start with? And so this is the problem that we wanted to fight. So yeah, and then our solution to that before I get to our solution to that, we use something, we help the semi-supervised learning process with another weakly supervised learning process, or supervised learning method, using the label ratios. So this was the big idea. So the idea is that while it's so difficult for a doctor to identify the exact regions that are what cancer, it's easy for the doctor to identify what percent of the slide is cancer, is what cancer. So the doctor can look at this slide, and maybe we can change like hours of work down to like minutes of work to say this is like 50% micropapillary and 25% papillary and whatever, right? It's a much easier label to create. And using this idea, we can guide our semi-supervised learning. And I'll show you how we do it. So the cool thing, or the way we did it, is we combined both the semi-supervised learning with the weekly supervised learning. So basically, maybe the next slide's better. So basically what we do is, in this process, when we use this model to predict the pseudo labels, it ends with a certain ratio, right? So this is the predicted cancer ratio. And in this case, I have 2 blues. But we know the true cancer ratio, right? The weekly supervised data, we know that there should only be 1 blue, for example, in this batch. So we know that there's something wrong. So the goal is we want to make the model make the predicted ratio closer to the true ratio. And we can do that by selecting, or like finding the samples that don't belong, right? So the predicted has 1 extra than the true ratio. So we can find, or we can use confidence, some measure to say that this one is probably wrong. This one is probably one of these other, that we don't know which one, but it's probably one of these other ones. So we can cut it out, right? We don't need it. We call it negative pseudo labeling. So we penalize the model for selecting this one in the first place, right? And we use some loss to train the model to prevent it from selecting this one in the future. And in this case, so obviously using these label ratios, we're able to get much better results, and we're able to do segmentation a lot better on this problem compared to many different methods. Okay, so data is only one part of what I study. So there's many problems with neural networks and machine learning, like computation problems, interpretability problems, security problems, and domain-specific problems. And this is a little promotion, but I work on all of these topics, but it'd be difficult to shove it into one presentation. So yeah. And of course, I have more promotion. I have many collaborations. So if any of you want to collaborate and you have data, I want your data. So I work on many different topics because interesting new problems are interesting for me and in my lab and my colleagues, because we want to do, help real people. We want to close the gap between real applications and machine learning theory, right? We want to help people solve their problems, and it helps us both. Anyway, okay, so thank you.
Thank you. Thank you very much, Brian. Do we have any questions?
Thank you, Brian. So can you say a little bit more about how you select this kind of, what is the figure-lets or shape-lets? There. Because I guess what is the strategy here? It's like wavelets, right? But,
yeah. Wavelets are, let's see, extra slides. Oh my gosh, I went too far.
And they are a bit like Fourier transformations. So was that the thought behind it?
That's a little bit. Wavelets are like Fourier transformations. They're a little bit different. So shapelets are just pieces of the time series. Wavelets are like convolutions, or they're like applied to time series. So it's a little bit different. But the way we use it, we use something called matrix profile. So matrix profile is an algorithm that finds patterns and anomalies. So there's something called discord, which is like an anomaly or discord, And so you can see in this signal, these are all the same, but this one is a little wider. So in this algorithm, we can use matrix profile to find that there's an anomaly here. Like this is different. And then so in the method we use this algorithm to identify these anomalies, these strange pieces, but we find it across a whole data set. And then these are the candidates. So these anomalies are anyway, these anomalies are found across the whole data set. And then once we have these candidates, then we can select which ones are meaningful. And we use some small classifier to identify that this one is meaningful to this class, but this classifier doesn't have to be good. It just has to make some kind of judgment. So it just says that this is meaningful because we want it to be fast. Otherwise, yeah. And then that's why we refine the candidates down to the top 10 meaningful ones for this class. And that's how we identify the discriminating shapelets.
My question was actually partially related to the shapelets and sort of the transformation of your data sets in the second examples. But these are essentially like eigenvector, eigenvalue decompositions, right?
Right.
You're finding key points. You're doing a dimensional reduction. Here it's 1D, so you're just looking at shapelets. In 2D, you have PCA of cartoons versus real images, so you can transform the data. So my question is, you mentioned at the beginning that we've shifted away from classical machine learning.
Right, yeah.
I've seen things like PCA called machine learning.
Right, no, it's just machine learning.
To some degree it is, right? That's the classical one.
Yeah.
And I find it interesting that all of the adjustments that we're developing on top of neural networks are classical in nature, right? You're not building an additional neural network to improve the neural network, right? The only way we can do it is by sort of fundamental, more interpretable mathematical processes.
Right, yeah.
So my question is, do you still think that for these sort of applications, AI still has neural networks and deep neural networks have a significant improvement? Or should we be actually looking at, well, if we can find these shapelets, well, what if we just use the shapelets themselves, do a Fourier analysis on those particular locations and build a recursive, like an RNN or a random forest model? Would that be as accurate as the sort of convolutional neural networks?
So, okay, so there's a bunch of questions in there and I'm gonna try to hit each one. So actually, there's something that, I don't know why I moved the thing. So there's something that you mentioned, the difference between classical and the current. So so come tomorrow, I'll explain neural networks. But actually neural networks are classical, like pieces, they have like, like, what do you call it? What is it? Like research is built on the shoulder of giants. Everything in a neural network is from classical. So like a neural network, this basic one, is just defining a line, defining the equation of a line, just like an SVM. And using layers is just like a inner product for an SVM. And using batches and like randomness, whatever, is the same as a random forest, right? So everything, it's actually classical. It's just hidden under cool words.
But I guess the difference is that those other methods are interpretable in the sense that I can trace it, but these you can't trace.
Right. Well,
you can.
But
it would take an impossible amount of time. So that's, I guess, how I define the difference between classical and new.
It's just the big difference, I think, is that it's this difference. It's the difference in data. So the cool part about neural networks is that it seems like if we throw enough data and throw enough compute at it, it'll get better. And it hasn't stopped. We just keep on throwing more. So like if you follow, for example, ChatGPT, the first one was like a few billion parameters. And then now it's like a few trillion. The only difference between them is small changes in training, but mostly bigger model, more data. And right? Just bigger model, more data. So unlike the other methods. So the classical methods, more data helps. Like in here, naive Bayes and I don't know, the other ones are maybe classical. More data helps, but more data is more difficult, also more difficult. So like to deal with. So for example, in SVM, being able to calculate all the distances between gigantic pieces of data is not reasonable, and noise and just so many problems. So one, the data is a problem. The other is, it just takes too, like with the size of data sets, some data sets, it seems like the classical methods are just too slow. And if we just keep on throwing weights at neural networks or throwing data with neural networks and get bigger and bigger, it seems to be, increasing. But we could do it in a easy way, like a way that we don't hit these memory constraints as much. Does that make sense? So that's the big difference between the methods. Is that, well, some methods not, like random forest maybe, and XGBoost, these two, you can just keep on throwing data at it and you can train more. But like things like SVM or KNN or other like original decision trees, you can't just keep on increasing data because you can't have, it'll take too long. Because then you have to do like measurements between every point, and it's just insane. Yeah, that helps. But anyway, there are interpretability methods. So I keep on switching through slides. So like there's a whole area called explainability, and so like this one in particular is called layer-wise relevance propagation, where we try to predict what part of the image led to the classification. And so there are methods to do it, and you're right, it's not totally transparent, and it's a big problem, and it's one of the 5 problems in neural networks. I even have a slide for it.
You mentioned one of the methods, data augmentation. Could you
Right.
give an example or explain a bit how you generate in the correct way?
Yeah. Oh my gosh, I think I deleted that slide. No, it's in a different presentation because I deleted because it wasn't so interesting. So here's a example of data augmentation. The most common is just you apply random augmentation methods. Yeah. Like for example, this image, we can rotate it or change the color or whatever. But there's a problem with data augmentation, and if you're curious on more, the big problem with data augmentation is that not all transformations are realistic. Like I've never seen an upside down cat in my life. So yeah, so this is a problem with data augmentation, but it's a problem people are solving.
In principle, you would like to sample from a random distribution that is underlying your data.
Right, that would be ideal, but it can't be perfect. Do I have? Oh, I don't have a slide for it. So it has to be from. So yeah, so you match some distribution, and you want to make new patterns, but there's a fight, because if you just sample from what you have, then nothing new will be created. And if nothing new is created, then the data augmentation is useless. So it has to be different from your distribution, but just slightly different, or just enough to make sense. Does it make sense?
Sounds a bit like art.
Yeah, but anyway, yeah. But unfortunately, in my field, many people just do this, and they just apply everything and hope for the best. But it's I have a conflict with this.
Okay, then I believe we are unfortunately out of time,
Okay.
but Brian is still around. And as he already mentioned, he will give a talk tomorrow at lunchtime to introduce large language models in general.
Yeah.
So that's also, if you have some colleagues who don't have any idea what's going on, that's suitable for everyone. And so let's thank Brian again very much.